Hi everyone, welcome back. Welcome to the new tutorials on Venturimeter. It is the experiment number 3, and it is a flow measuring device. You can see on the this plot here. It is called Venturimeter, and this Venturimeter is efficient device to measure flow for a pipe. So today I will discuss about this Venturimeter, and we'll see how to make this device as a metering device. We'll calibrate this one and we'll test the efficiency of this flow measuring device. Okay, so for a flow measuring device, why it is called Venturimeter? We can see here, right? We have a section like this one. Water is flowing from a left to right with a velocity V and Q. Flow rate is Q. And we can see we have a converging section right here. We have a converging section. It is called converging section. Okay, and then we have a smallest constricted throat section, and then we have a diverging section, diverging. Okay, then we have again straight pipe. So what is actually happening here from the Bernoulli's principle? You know, if the cross section is narrow, then what will happen? The velocity will be higher and the pressure will be lower. So what is actually happening? If we insert one piezometer here, that is already there, right? Piezometer here, and now the section is converging smoothly here. Then we are inserting another piezometer here. We're calling this smallest diameter section as throat section. So we are inserting another one. And what is actually happening here? So the velocity at this point, this will be increased, right? When it is converging, velocity will be increased. That means the velocity head is converting, means velocity is increasing from pressure to velocity. So at this point, see, pressure is here, and at throat section, pressure is lower. However, the velocity is higher, right? In order to make the total summation constant, right? Even though there will be some head loss. So according to Bernoulli's principle, the total summation of the velocity head and the pressure head will be constant if we neglect the head loss as well. So the converging section, within the converging section, the pressure head is converting to velocity head, and then we have another section that is diverging, right, this way. So at the diverging section, the velocity head is again converting to pressure head as the cross section of the conduit is increasing. So if we combine them together, this converging section and the diverging section, then it is called Venturimeter, and this device can be used as a flow measuring device. If we just insert this Venturimeter on the way of a pipe, so since it is a pipe and then we are adding a Venturimeter, this part is a Venturimeter, then we can measure the flow. What is the flow rate through this pipe? So now we'll see how to measure the flow. We know the Bernoulli's principle. We'll apply this Bernoulli's principle here. Since we already have a piezometer here, right? We have a piezometer here and we have another piezometer here. So at section number 1, we're considering this as section number 1, and this is section number 2, and this is point number 1, and we are considering that this is a reference level. Okay, this is a reference at the center of the pipe. So from this reference level, we're measuring everything. So that's why we don't need to add any elevation head G1 or G2. So these are perfectly horizontal. So if I just try to write the Bernoulli's equation, and before that, see, if we just consider that piezometer, water is here. This is the P1, right? P1 by gamma. And then if we add velocity head, if we consider velocity is V1 here, then we are adding this velocity head. Then we are getting the total energy, right? And then at section number 2 here, if we just consider this part, it is basically P2 over gamma. And then if we add velocity head here, we are getting the total head at this point. And it is, we're just extending this line. And still you can see there is a difference, right, in between these two lines. It is called head loss. Since there is a head loss, that we can calculate that, and we already have idea about head loss from Bernoulli's principle. It is nothing but the application of one of the applications of Bernoulli's principle. We can clearly see that. So how can we make a relationship, if we make a relationship between this pressure differential, here we can see you can see here clearly. I'm just trying to focus that one. That is the difference between the pressure head, not the velocity head, or not the total head, right? So that's the difference between the pressure differential. It is called pressure differential in between section 1 and section 2. So we'll make a relationship in between Q and that pressure differential, and then we'll be able to measure the flow, right? So the relationship will be something like this one. Okay, let's see. Let's derive that relationship, and then we'll understand how can I derive that one. So if we apply the Bernoulli's principle in between point 1 or point and point 2, then what will happen as before, right? That will be basically, there is no elevation since we are measuring everything from the center of the pipe. So the elevation is the same at 2 points, and that will be cancelled out from both sides. Then we'll have a P1 over gamma plus V1 squared over twice G is equal to P2 over gamma plus V2 squared over twice G, right? So that's the total head at section number 1 and section number 2 from Bernoulli's principle. And another thing you have to consider that, see, at section number 1, we know the pipe diameter D1, and we also know the pipe diameter D2 at this throat section, right? This is called throat section. We have to consider that one. That is a very important part of this device. And we know from this continuity equation, right, Q is equal to A and V. We know that. So from that two section, we can apply, since we know that Q is this one, is same for Q in and Q out. There is no flow diverting, or there is no loss of flow. So everything is same, Q in and Q out, it's same. So we can write Q is equal to A1, V1 is equal to A2 and V2, okay? And from this relationship, what we can do, we can write V2, okay? V2 is equal to A1 and V1 and A2, okay? We can write this expression. And we also have this Bernoulli's principle, okay? Let me just quickly show you this one. If I can insert a new page, and let me just show you. Okay, so we maybe we have one new page. Wait a minute. Not this one. Okay, so we have this equation, and from this equation we can just derive quickly. Okay, then I'm going back. So we already have A1, we have V1 is equal to, we have A2, V2, and from this equation we can write V2 is equal to A1 of V1 and A2, right? And we know the diameter, and then since you know the pipe diameter and the section is circular, if you know this diameter D for A1, it will be pi over 4 D1 square. This is the cross-sectional area for circular section. You know that very well, right? And let me just hide everything so that we can, okay, we have wider place here. And what we can do here, see, for A2, we can even write the equation for third section, that is the area, okay? And from V2, from that equation number 1, we can write V2 is equal to, right, pi over 4 D1 square and V1. And then we'll have pi over 4 D2 square and nothing else. So this pi over 4 and pi over 4 will be cancelled out. So what we'll have d1 square v1 and d2 square. So v2 is equal to this one. And by this time we already have the Bernoulli's principle, p1 over gamma plus v1 square over twice g is equal to p2 over gamma plus v2 square over twice g. So our main purpose is to relate these two equations. Okay, this is equation number 2 and these two equations. So how can we do that? All right, we can put v1 square here and then twice g, and we can bring that v2 from right side and we can write this way. Okay, we can do this way, or we can even make it reverse if we want to determine the pressure differential for v1. Okay, we can do even differently. Since we have v2 here, so we can write the expression this way. We can write p1 over gamma minus p2 over gamma, because we have the higher pressure on the left side, and then at section number 2 we have the lower pressure. That's why we're making this difference. And then we can put it this way as well. You can do even whatever you want, it will be same. Since I already calculated v2 here, then I'm just trying to bring v2 here. So see, we have this one. So that's the expression, p1 over gamma and p2 over gamma. So that could be replaced by h. So that's the pressure differential. We can say this is the h. We'll denote that one. And then we have v2, right? We have v2. The v2 is v1 square over, this one is the v2. And before that we can do 1 over twice g and v2 square minus v1 square. So what we can write, v2 square minus v1 square, and then if we multiply this twice g, and we will have p1 over gamma minus p2 over gamma, right? And then we can even replace the v2 with that one, d1 square v1, right? d1 square, since it is square and divided by what? d2 square. So since it is v2 square, we are replacing the values of now v2, so that's why it will be squared, and v1 squared is equal to twice g. So p1, okay, p1 over gamma minus p2 over gamma. And then what will happen? Then we can write, we'll have d1 to the power 4 v1 squared, and then d2 to the power 4 minus even v1 squared is equal to twice g p1 over gamma minus p2 over gamma, right? I'm just cleaning some space here so that I can repeat. Okay, so we have this formula. So from this part, d2 square, I can even assume v1 square. I can take v1 square out of this one. So I'll have d1 to the power 4, and then I have d2 to the power 4 minus 1 is equal to 2g, and p1 over gamma minus p2 over gamma, right? So if I put now v1 square here, then what I'll have 2g, I'll have 2g, and I'll have d1 to the power 4, I'll have d2 to the power 4 minus 1 here, into I'll have p1 over gamma minus p2 over gamma there. Since it is v1 square, I basically wanna take v1. So v1 will be root, right, square root, and twice g. If I just clearly write this way, this is the ratio, we have the same exponent, right, the power, minus 1, and then we have P1 over gamma minus P2 over gamma, right? This one. So that's the velocity. That's the velocity at section number 1. See, you can see at section number 1, that is the velocity. If we know, right, if you know the diameter D1, if you know the diameter D2 at throat, and if you know the pressure differential here, you can easily calculate the velocity at section number 1. Once you have the velocity, and if you know the cross-sectional area, you can easily calculate the Q, and Q is same everywhere. So that's why Q will be A1 and V1. You can calculate Q by that way, A2 or V2, but we need to derive the same expression for this expression for V2 as well. You can do that. It is simple. The answer will be same. So that is the expression for V1. So let me just consider another term, because the equation looks pretty complex, right? So what we can do, we can even simplify. We can even simplify, because for perfect or for any specific Venturimeter or setup, D1 and D2, right? These are constant. This won't be changed for any device. D1 and D2, this will be fixed. Since this will be fixed, there will be no change. So what we have to do, right? So this D1, or let me just quickly go back to the previous stage. Okay. Since this D1 and D2 are constant for a specific device, so this ratio will be constant. And if we make power to the power this D1 and D2, this will be constant. That means I'm just trying to say this value will be constant, right? This entire thing will be constant. So we can replace this to make the equation simple. We can replace this value as K, right? That's why I'm gonna make this equation simple, right? So how can we do that? So I'm writing V1. So V1 is equal to K, I'm giving K1, that is K1, right? And I can replace that P1 over gamma minus P2 over gamma is equal to H, because that is the pressure differential, okay? And I'm replacing this part, including that square root. But for this one, I'm replacing only this one. So that's why we'll have H to the power what? Half, right? For a square root, it is half. And I'm replacing that K1. So the value of K1 is this one, 2G divided by D1 and then D2 to the power 4 minus 1. So that is the value of K1, and that is the value of H. And then I have the V1 here. So that is the expression for V1. Now I'm calculating the theoretical discharge QT, right? The discharge we're calculating using this theory, all this derivation and equation. These are called a theoretical discharge. So QT is equal to A1 of V1. Since we have the value of V1, so we can write A1, K1, and H to the power half, right? And since A1 is also constant for a specific setup, because it is a pi, A1 is nothing but A1 is equal to pi by 4 and D1 square. So it is a constant value for any, because the diameter is fixed, we are not changing. So we can replace A1, K1, this A1 and K1 by K and H to the power half. So that is the theoretical value of flow rate or discharge, right? So that is the equation we can use to calculate the theoretical discharge, this one. Once you have the value of K, and then we can calculate K from A1, K1, and we can calculate K1 using that expression, right, including that square root, and then we can calculate QT, right? So once you have QT, we also need to calculate QA in order to check the efficiency of the device. How can you check that? So from this equation, you can get the theoretical, right? Theoretical flow rate. And if we somehow know that actual flow rate, then we can make a ratio, right? We can make a ratio in between theoretical and this one, in between actual and theoretical. So that will be the efficiency of the device, and we are also calling this one coefficient of discharge. So how can we calculate this QA? Since I already know what is flowing from left to right, and we are collecting this water, right? We're collecting this water in a bucket as before. This bucket, the dimension of the bucket is same as before, 30 into 30.5 into 45.5, and we're collecting the water, for example, for 10 centimeter. Then we can calculate the volume, and from the volume we can calculate QA, right? V divided by T. We'll see the calculation. So somehow, if we know the actual flow rate, right? Actual flow rate from V divided by T, then we can calculate that coefficient of discharge. Once we have that, we know that this efficiency should be 0.99 for a larger flow measuring device or Venturimeter, and for a smaller one, this should be 972, 0.98. That means 98% and 99% should be the efficiency. Then we can use this flow measuring device for practical purpose. And this device is basically useful for not only incompressible fluid, not only to measure incompressible fluid like water, but for compressible fluid as gas and other fluids as well. But only disadvantage of this device is the head loss. It has a constant head loss, because what we are actually doing here, we have a converging section here and we have a diverging section. That's why there will be head loss here, head loss, and there will be bubble. You can see some bubble. We can call it cavitation, and because of that, and because of the roughness of the glass or the material that is using, right, that is being used for the construction of the device, because of the rough surface, there will be head loss as well. So this is how we can test the efficiency. But there is another objective of this experiment is to calibrate the device. Calibration means we'll make a definite relationship in between that Q and the flow rate with the pressure differential. So main objective is we just want to know this pressure differential. By knowing this pressure differential here, we want to know the actual flow rate, not the theoretical. We don't want theoretical flow rate, right? We want actual, what the actual flow rate, right? What is the actual flow rate? We want to know that. And in order to know that, we want to make the equation simple only by understanding the difference between this level and this level. So how can we make that equation? Let's see. We can proceed with the equation, and then we'll calibrate, right? Calibrate our device. Calibration means we'll test our device for different condition, and then we'll prepare an equation, and based on this equation, we'll measure some parameter exponent, and then we'll create or generate or develop an equation. And ultimately, we don't want to calculate every time we take the reading, other than taking and calculating every time. We can take the reading, and we can even check the graph. We will make the flow measurement as simple as possible. Let's see, how can we do that? So since we already have this equation, right? CD, we have this equation. CD is equal to QA actual, because we want to make the relationship in between actual flow rate with the pressure differential. So that's why we have to put QA here and CD into QT. By this time, we already know that what is the QT, right? It is nothing but what? Here, we already know K, right? It's K H to the power half. Since CD is another constant, a value, right? It may be 0.99 or 0.98, whatever the value is. It is a constant. K is also constant. We already have idea, right? K is nothing but K is K1 and A1. We know that K1 is also constant. It depends on the diameter of the two and the ratio of these two diameter. So that's how we can even replace these two value again. So QA will be C since we are replacing this CD into K, now we can't even write this to the power half. This should be an unknown value because the equation is looking like this expression, right? QA on the left side is equal to some constant value and then h to the power and constant. But the reality, see, theoretically this value is half, but in reality this may not be half. This may be different. So that's why while calibrating this model, we have to find out these values of n and these values of c. If we somehow calculate the values of n and c, and if we can replace these values here, like it is maybe 110, okay, and then h to the power maybe 0.46 or for anything. So that will be the calibrated formula for this specific device, because we'll test this device for different flow condition and we'll use those values to find this exponent n and the coefficient c. Then we'll replace those values in this equation and then we'll have a equation like this. So if we somehow prepare this equation and then we can read from the flow measuring device, right? And if we can use this value of h, we'll directly get the values of QA, right? If we calculate from this equation, that is possible. But we don't want to use calculator every time we want to get the value. We'll plot a graph and we'll paste the graph in front of the flow measuring device. Then we'll only calculate or we'll only measure this pressure differential, and from that graph we'll measure directly that QA. So then life will be easy, right? So let me just quickly show you how to calculate these values of n and c. So that is another objective, to calibrate this model. So since this equation is not a linear equation, it's kind of parabolic form, right? It's a curve. So we have to make some changes there, okay? To make some change. So the equation is this: QA is equal to C h to the power n. So we have to make it linear in order to plot and in order to get the value of n and c. How can we do that? We can use log on the both sides, right? QA is equal to, we can use log and then c h to the power n. Then we can further even simplify log c, since it is multiplication, and in log we know that it will be plus h to the power n. Again, we can simplify log c plus, since it is power, then n will come first and then log h, right? And then on the left side we have log QA, right? So that is the expression we have. So can you just imagine how it looks like? It is nothing but y is equal to c plus mx, right? You know as equation y is equal to mx plus c. It is the same equation, right? Y is equal to mx plus c, and it is a general form of a straight line. And if we plot this straight line, y is equal to mx plus c, it will look like this one. And the slope of the line, this is the slope of the line m, and this, right, this segment or intercept of y-axis, it is called c, and that is the x-axis and that is the y-axis. So if we just make, now we can see the similarities between this equation and y equal to mx. That means y is equal to log QA and c is equal to log c, and then m is equal to n, and then we have x is equal to log h. That means these are similar. So somehow if we just test our device with different q, right, we'll have different QA, like for 5. If we have 5 groups, right, we can start measuring the QA for 5 different groups. And if we just make a table, we'll have 5 different differential values of pressure, and then we can use that. But how can we plot that log QA than log h? We need to use a log paper. The x-axis should be log axis, right? Instead of this one, we have to use log axis, right? Here we have to use log. So we have to plot this way, log h, and then log qa. Then we'll have a equation, a straight line like this, and from this straight line we'll calculate the value of slope, right? We'll calculate the slope, and that slope will be n. Okay, so how can we calculate slope? We already know if we have idea about straight line, right? So we know the slope of any equation. It is what? It is the tan theta, right? It is the tan theta is equal to slope. If that is the straight line, and if you know the ordinate of this point and this point, these 2 points, right? If that is basically x1, y1, and if that is x2, y2, means that is the x, okay, that is x1, and that is y1, and from this one it is y2, and from this one it is x2. So if we take the difference, we need this part because we have point this one, so that will be y1 minus y2, and this will be x1 minus x2 or x2 minus x1, whatever it is. So tan theta is equal to slope is equal to y1 minus y2 divided by x1 minus x2. If we take log of this one, if we plot in a log scale, so instead of taking that y1 minus y2, we have to take log y1 minus log y2 and log x1 minus log x2. So for our case, if we plot in a log graph paper, right, and we'll have 2 different values of, we'll select 2 points, and then we can compute the slope. So what will be the slope for our case? Because for our case, we'll have log h here, and we'll have log qa, and we'll have one straight line like this. If we just calculate, or somehow we got 2 points, right? So from these 2 points, we can even compute qa, right? This will be qa1, this will be qa2, and this will be h1, this will be h2. Since it is a log paper, the value if I extract from this graph paper, it will be log h1, log h2, and log qa, and log qa2, right? So what will be the slope of this line? N is equal to the difference between, so log qa1 minus log qa2 divided by, it will be log h1 minus log h2. Okay, since it is log and it's minus, so we can write log qa1 divided by qa2 and whole divided by log h1 divided by h2, right? So from this equation, we can calculate the values of n. Once you have the values of n, we already know, right? The main equation qa is equal to c h to the power n. If you know n, it will be something like 0.5, but 0.5 is the theoretical value. So from the experiment, it could be 0.46. So it is acceptable from 0.45 to 0.55. So if it is within this range, that means your experiment is okay. Then using any one, right? So using any value from that previous 2 points, from this point or this point, or you can find another third point, and you can validate this equation using that third point, like this one, qa3 is equal to c h3, and then values of the n like 0.45. So we know this h3 and q3 and n, so you can calculate c. So this is how we can calculate. So let me show you that all these calculations, then you will understand what I'm trying to say here. Okay, and then we'll talk about that. So here we have our data sheet. See, so this data sheet, it is same as previous one. This calculation, you can see the bold, right? So that are already measured data, the size of the tank, it is as before. So we can even calculate this area, 45 into 30.5, it is giving me 1372.5 centimeter square. We have the diameter D1, right? It is already given since we have a device, and the D2 at throat section, it is constricted section, and we're measuring the temperature of water because we'll calculate the Reynolds number. We'll do that. And then we also have the initial gauge as before, and we also have the final gauge 10. So what will be the total volume of water, right? The total volume of water V will be that 1372.5 into 10 means as before 1372.5 centimeter cube. And what will be the area of the section, right, at 1? So that this one, so it is nothing but A1 will be pi over 4 and D1 square. So we know that 3.1416 divided by 4, and what is D1? It is 3.175 and squared. So 3.1416 divided by 4 multiplied by 3.175 squared, and we are getting 7.9173 centimeter square. And same for A2. If we calculate A2 here, A2 is equal to pi over 4 into 1.5875 squared. So let me calculate that quickly. 3.1416 divided by 4 and multiplied by 1.5875 squared. So we are getting 1.979 centimeter squared. Okay, we are getting this one. And we are also calculating from table this viscosity of fluid at 28 degrees Celsius temperature. So when we had this experiment, so our room temperature was 28 degrees Celsius, and for 28 degrees Celsius, you can see the right at the back side of any fluid mechanics book, you can get the value. And if we don't have the value for 28 degrees Celsius temperature, you will have value in between 26 or 30. You have to interpolate, right, to get the value at 28 degrees. So that is the viscosity. It is called kinematic viscosity. Then let me just show you the calculation. So volume of water, we know that the volume of water is that 1372.5 centimeter cube, and we know the time, we get this time from experiment, this one. So what will be the actual? It will be 113.725 divided by 58.3. So we are getting 235. Okay, we are getting 235, 235.42. okay, 42. So that is the centimeter cube per second actual flow rate for that specific group. And then on the left piezometer, right, we have this value 81.8, and on the right one at the throat we have 72.9, and the difference is 8.9 centimeters. So that is the H. We know the H, right? Then we have to calculate K1 and K. We can calculate that. Okay, here's the equation. We know that. What is K? Now we know K1. K1 is nothing but this one, 2 into G, right? G is 981, since it is in CZ S unit, everything is in centimeter. Then we have D1 and D4. D1 is 3.175, okay, 3.175, and D2 1.5875, 1.5875 to the power 4 minus 1. So that is the value of K1. Let me just calculate that one. 3.175 divided by 1.5875, right, to the power 4 minus 1. Minus 1 and 2 into 981 divided by this value. And if we take the square root of this entire thing, we'll have 11.436. We have 11.436. Okay, 11.436. So what is K? We know that the K is equal to A1 and K1. A1 is the area at section number 1. So what is the area? Area is this one, 7.931, right? 7.93, 7.93, 9173, 9173, 9173. Okay, 9173 into 11.436. This one into 7.9173. So we are getting this value 90.548. So 90.548, that is the value of K. 90.548. And if we know that K, we can, so that is K, right? That is K. This is K or V1. What is the value of K? Let me check it again. Value of K was what? That is the value of K. No, it's this one. Value of K is K1, A1. Yeah, we have K1, A1. Once we have A1, K1, we can calculate. We have the H, right? Where is the data sheet? We know that that is the K. We have K. Then QT, right? We know QT is equal to K h to the power half. That is the expression for. So we know K is 90.548 and H, right? We know the difference 8.9. So 8.9 to the power half. So this one into 8.9 to the power 0.5. So we are getting 270. Okay, 270 to 70.1, 270.1. So that is the theoretical value of flow rate, and we have QA. So we need to calculate CD is QA over QT. So actual velocity, we didn't calculate that because we already calculated the flow rate. So 235.4 divided by this theoretical, so we have 0.87. Okay, so we have 0.87. That is the efficiency, 87% efficiency we have. So again, we can calculate V2. So what will be the V2 at the end, right, at the throat section when it is restricted, when it is constricted, right? We don't need to calculate V2. So V2 is equal to QA. We need to calculate the actual velocity V2. That's why we are using this velocity 235.4, and the cross-sectional area at throat section. What is that? It is 1.979, right? This one. So from that, 235.4 divided by 1.979, so it is giving us 118.9, because that section is so constricted that the velocity is too high, 118 centimeter per second, right? 1.2 meter per second. It is so fast. Water is flowing so fast. So that is that. So we have to calculate the Reynolds number. Do you have any idea about the Reynolds number? We know that Reynolds number NE is equal to VD divided by nu. Nu, right? Nu is the kinematic viscosity. So we have VD. V is the velocity of flow at that point, right, where you want to calculate that Reynolds number, and D is the diameter at that point. Since we are trying to calculate the Reynolds number at section number 2 there, at section number 2 there, so we need to know the velocity at this section, right? We need to know the velocity at this section, and at the same time we need the diameter at section number 2. So then we can calculate the velocity, we can calculate the Reynolds number. So Reynolds number is basically a ratio of Vd over nu, and in plain English we can say it is the ratio of inertia force to the viscous force. That is the definition. Okay, inertia is the ratio of inertia force to viscous, from viscosity, okay, viscous force. And this Reynolds number, it determines whether the flow is laminar, okay, laminar, transitional, or turbulent, okay, or turbulent. So we have a range, right? If the velocity, if Re, if this value is less than 2000, then the flow will be laminar. Then flow will be laminar. When the streamlines are parallel to each other and they are not touching, that means when the flow is smooth, so smooth that they're not touching anyone, it is just smoothly flowing, then it is called laminar flow. If the Reynolds number, this Re, is greater than 4000, then the streamline will be like this one. There will be collision in between these streamlines. Then it is called turbulent flow. And if the Reynolds number in between 2000 and 400, so it will be transitional flow, the flow state. This is basically determining the flow state, right? So let me just calculate the Reynolds number. We know Re is equal to, so V2, and it will be D2 and then nu. So we know the V2 is 118.9 centimeter, and then we know the D2 as 1.5875. And what is the value of kinematic viscosity in terms of centimeter? 0.8372 into 10 to the power minus 2. If I just try to calculate this one, 1.5875 divided by 0.8372 and that 100. So what we have this value 22,505. So it is more than 22,000. That means the flow is definitely turbulent flow. So the experiment we did, most of the river flow or most of the pipe flow, these will be turbulent flow. So we know the state of the turbulent flow. Then what we are trying to do now, we have to go for that calibration, right? Calibrating that Venturimeter. Then what we need to change the condition. The calculation we just saw is only for one flow condition when the Q is for a certain group, and then we are changing the Q for 5 times. We have group number 1, 2, 3, 4, 5. Then we are calculating the same QA, actual flow rate, and then we are also calculating the pressure differential for each of these groups, right? So we need this information, and we're showing here also the coefficient of discharge for each of these groups and the Reynolds number for each of these groups. So you can see the flow rate here is maximum, then the Reynolds number is also maximum, right? And also you can see flow number is also increasing, and then Reynolds number is also increasing. Then flow rate is decreasing, Reynolds number is also decreasing. So that means if the flow rate increases, then there will be more collision in between the streamlines, and then the flow will be more turbulent, right? Okay, so having said that, we can go for that graph and we can calculate that exponent of this equation. So we have this equation for that device. We already derived this equation, C h to the power n. We need to know C and n, then we'll have our calibrated device, and we can use that device for flow measuring purpose. Okay, so we have to plot. You can buy this type of graph. It is called log graph. You can see we have a log scale along x-axis. We can see, right, it is repeating at this one and this one. If you want to read log scale, how can you read that? See, if that value is 1, so that is 2, 3, 4, 5, and that will be 10, and that will be 20, it will be 100. If this value is 10, so this is 20, this is 30, and this will be 100, 10 times. It is repeating, right? When it is repeating, it will be 10 times since it is log, and this will be 1000. And similarly, we have the same value along this vertical axis, right? If it is 1, it is 2. If it is 10, it will be 20, and then it will be 100. So this is how we can select our scale based on our data. So we have to plot. H, right? We have 5 values of H, and we have head difference. We have to plot H this way, so it will be log H, right? Since the graph is log graph. If you plot H along x-axis, it will be log H, and if you plot QA there along y-axis, it will be log QA. So what I have done, I just, instead of selecting this type of paper, I plotted this graph using Excel. See, and then I have this plot like this. I use Excel and I have a plot like this, and from this graph I can calculate the values of, right, N and C. So that is the line, this blue line, you can see this blue line. So I plotted this 5 point. I have point here, right? I have point, 1 point here. I have 1 point here. I have another point here, another point here, and here. And then after finding this point and marking this on the graph, I'm just drawing a average line, right? Drawing an average line, that is C, following is putting some point on the left side and some point on the right side. So it is an average line, because these points are for one group. Maybe each group, they may make mistake, right? That's why I'm taking average of all groups. That's why the line is passing through middle of all these lines. Okay. And then the next step, we have to exclude these 5 points, because these are the experimental point. We have to find 2 points other than these 5 points. So I'm selecting this one. See, I'm selecting this point where we have a intersection, 2 lines. Between 2 lines, we can easily get the reading accurately, because it is a log scale. If you have any value like this, how can you differentiate? Because C is gradually increasing or gradually decreasing. So that's why it's better to find the points that are basically intersecting. So here we have intersection, and if we go here, we can easily get the value of this point H, and corresponding to this one, we can get the value of QA. So what will be the value of H here? Since it is 10, right? This point is 10. It is 1, 2, 3, 4, 5, 6. So it is 6. And then the corresponding value of QA, that one, this is 100, this is 200, 300, and then this is 1000. So that will be 200. Okay. And for this point, if we mention here, what is the value of H? Again, 10, 20, 30, 40, and this is 50, right? And that is 100. And what is the corresponding value of Q here? That is 200, 300, 400, 5, and 600. So that is 600. So we have 2 pair of values, right? 2. The first one, at first it will be H, right? It will be H1 and QA1. And we have what? 6, 200. And we have another point, H2, QA2, and we have this value 50 into 600. So using this 2 point, right, 2 points, we can calculate the slope of the line, this slope of these 2 lines, the slope of this line, right? Slope of this line we have. So what is the equation we just saw? N is equal to log, it will be QA1 divided by QA2, and then log H1 divided by H2. So if I put these values in the equation, then we'll have 200, means log 200 divided by 600 and divided by log 6 over 50, right? Then let me just calculate this one. We have log 200 divided by 600, and then whole divided by log 6 divided by 50. So we are getting the value of N as 0.0 0.518. Since we already have n, we know the equation QA C h to the power 0.518. Okay, so how can we calculate C? We can calculate C by using this point or this point. That's what I said, or we can even find third point. It is okay to use this point, no problem. So QA is a 200, you can use second one as well. And then C is unknown, and then H is this one, 6 to the power 0.518. So what will be the value of C? So it is a 6 to the power this value and 200 divided by this one. So we have 79.04. So the equation becomes, right, Q calibration, this is the calibration equation, 79.04 and H to the power 0.518. So that is the calibration equation for this specific Venturimeter, right? So if you know this equation for this specific Venturimeter, so it is not, this equation is not for any other device, because we calibrated this device only for this diameter and for this setup, right? So if we know now, we have the equation ready. It is relating actual discharge with the pressure differential, and if you measure that pressure differential H, then you can put it. Now, for example, we are measuring what is flowing. We have the device, right? We have the device here. We have the device and water is flowing. Okay, we have the device here. Water is flowing. We are measuring this one and we are measuring this one. We can quickly measure that. Okay, we can quickly measure that, and we can calculate H quickly. P1 by gamma minus P2 by gamma, and we can directly put this, right, in this calibrated equation that we just made right here, this equation, right? For example, we have H is equal to 100, the pressure differential 100. We want to know what will be the, this is centimeter, flow rate, actual flow rate. So QA is equal to 79.04 into 100 to the power 0.518, right? This one into 100 to the power 0.518. So I have the flow rate. It is 858.68. So that is the flow rate, this centimeter per second, and this flow rate is actual. So thank you very much.